With the utility of the inverse trigonometric functions, in addition to the tool of the unit circle, we are well equipped to begin solving basic sine, cosine, and tangent equations. In this video, we're going to focus on basic sine and cosine equations. Keep in mind, we are leaving identity equations, moving into the territory of conditional equations. So now would be a good time for a formal definition. Recall that an identity equation is satisfied by all values of the variable for which both sides are defined. So really, an identity equation sets two different looking expressions equal, though they represent the exact same concept. On the other hand, a conditional equation is an equation that has at least one solution but is not an identity. Let me clarify the distinction with two algebraic examples. An identity from algebra might look something like this. 2x minus x equals x. Both sides represent the exact same expression, and we would find that every number from negative infinity to infinity would balance that equation. On the other hand, a conditional equation from algebra might look something like this. 2x minus x equals 5. In this case, only the value x equals 5 would balance that equation. We could say that equation is true on the condition that x equals 5. So in section 4.2.1, we will examine equations that contain a sine or a cosine that have specific solutions. That is, they'll be true on the condition that x attains a certain value. And just as you learned specific procedures or algorithms for solving different types of algebraic equations, we're going to follow a procedure, a process, or an algorithm for solving basic trigonometric equations. To find all solutions to a basic sine or cosine equation, do the following. Number 1, isolate the trigonometric function. Number 2, apply the appropriate inverse trigonometric function to both sides to isolate the argument. So number 1, get the trig function by itself. Number 2, get the argument by itself. That's going to require an inverse trig function. Then number 3, find the smallest positive value alpha on the unit circle that makes the equation true. Your knowledge of the unit circle at this point will come in very handy. Then we're going to look around the unit circle for any other value, let's call it beta, if it exists, which may or may not, on the unit circle that also makes the equation true. Then number 5, express the complete solution set as the set of all x such that x equals alpha plus 2k pi. Alpha is the first smallest positive solution that we find on the unit circle. If we add 2k pi to alpha, we're looking at all angles that are coterminal with alpha, which would also balance the equation. Recall that beta was the second solution that we found on the unit circle, which may or may not exist for all equations. If we add 2k pi to beta, we're finding all angles coterminal with beta, which would also balance the equation. And then we always specify that k is an element of the integers. Now, you may or may not have seen this symbol before. The upside down A means for all. It's called the universal quantifier. So that simply means for all integers k. All right, I think that's enough explanation. Let's get our hands on the details in example 1. Notice the instructions say find all numbers that satisfy the equation. We will look at restricting the intervals soon, but for now we're going to find every possible solution to these equations. Example A is cosine of x equals 1. Notice the trigonometric function is isolated, so to solve for x, we need to apply the inverse cosine to both sides. So x is equal to inverse cosine of 1. Now, I find it tremendously helpful to visualize the unit circle as you learn how to solve basic trig equations. So I'm going to use this as a tool to help us evaluate inverse cosine of 1. So we need to figure out an angle on the unit circle whose cosine is equal to 1. Recall that x equals 0 or x equals 2 pi has a 0.10 on its terminal side. So cosine of 0 equals 1 and cosine of 2 pi equals 1. So our first solution here is x equals 0 radians. But also, we know that if we rotate once around that unit circle and we land at 2 pi is also a solution to that basic equation. So in this particular instance, our solution would be the set of all x such that x is equal to, now if I did 0 plus 2k pi, notice that's equivalent to 2 pi plus 2k pi. These are all angles coterminal with 0. So in this case, it is sufficient just to say that our solutions are any multiple of 2 pi. So x equals 2k pi, where k is an element of the integers, is the complete solution set to that basic trigonometric equation. So again, the solution is 0 or any angle coterminal with 0. Let's try that process on example B. The equation is cosine of x equals 0. The trigonometric function is isolated, and we can solve for x by applying inverse cosine to both sides. We obtain x equals inverse cosine of 0. So we need to find every angle on the unit circle whose cosine, or x-coordinate, is equal to 0. One possible location where cosine is equal to 0 is at pi over 2. Recall the ordered pair here is x equals 0, y equals 1. Another possible location would be at 3 pi over 2. Recall the ordered pair on the unit circle here, x equals 0, y equals -1. So both pi over 2 and 3 pi over 2 have a cosine value of 0. So our solution set is going to contain both of those angles in addition to any angle coterminal with those locations. So our solution set will be the set of all x such that x equals pi over 2. That's our first smallest positive solution, plus adding a multiple of 2 pi will express every angle coterminal with pi over 2. Or we can do the same thing with 3 pi over 2. Another solution is 3 pi over 2 plus any angle coterminal with 3 pi over 2, and we have to be careful to specify k is an element of the integers. So there is an infinite number of solutions for this equation, but it is not an identity equation. It's only true on the condition that x is an angle coterminal with either pi over 2 or 3 pi over 2. All right, this takes a little practice, so let's look at example C. Cosine of x equals square root of 3 over 2. The trigonometric function is isolated. Let's go ahead and isolate the argument. So x is equal to inverse cosine of square root of 3 over 2. So we need to find an angle or angles on the unit circle whose cosine or x-coordinate is equal to square root of 3 over 2. Notice the value of cosine is positive square root of 3 over 2. Cosine is going to be positive in quadrant 1, and in particular, pi over 6 has an x-coordinate of square root of 3 over 2 on the unit circle. So one possible solution is pi over 6. Also note that cosine is positive in quadrant 4. If we think about the reference angle pi over 6 here, the corresponding angle in quadrant 4 is 11 pi over 6. So the solution to this equation is going to be the set of all x such that x equals pi over 6 plus any angle coterminal with pi over 6. We express that as adding 2k pi. Or the second solution, 11 pi over 6 plus any angle coterminal with 11 pi over 6. And once again, we specify k is an element of the integers. So that is the complete solution for that simple, fundamental, basic cosine equation. It has an infinite number of solutions. Let's try one more cosine equation with a bit of a twist. Example D is cosine of x equals 0.1. Notice we're dealing with a value that is not a common unit circle coordinate. So we're going to have to really think about this one. The procedure is going to be the same. We're going to isolate the argument by applying inverse cosine to both sides. However, because point 1 is not a common unit circle angle, we're going to need to approximate this with our calculator. Now, be sure that you're in radian mode to begin with, and then evaluate inverse cosine of point 1. And we're just going to approximate this to the nearest tenth. So our first solution is approximately 1.5 radians. I'm going to follow the same procedure that I've been using in visualizing these angles on the unit circle for assistance, but it's a little more challenging with radians. Now remember, this is 0 radians and 180 degrees is 3.14 radians. Pi over 2 is approximately 1.6 radians. So 1.5 radians then is going to be somewhere over here in quadrant 1. Now, another way to determine the location of that radian measure is simply to convert it to degrees. Remember, you can multiply a radian measure by 180 over pi to convert it to degrees. So we're dealing with about 86 degrees. So again, that can help you to visualize the quadrant in which the terminal side of this angle lands. So our first positive solution in the unit circle is 1.5 radians. But we also want to consider where else on the unit circle is cosine going to have a positive value. We know that's in quadrant 4. So we need to figure out the angle represented with a reference angle of 1.5 radians. So I'm going to think about starting at 2 pi and rotating 1.5 radians in the negative direction. And I'm just going to approximate this with my calculator. 2 pi minus 1.5 radians gives us approximately 4.8. And I'm just rounding to the nearest tenth here. So the solution to this equation will contain both 1.5 and 4.8 radians plus any angle coterminal with those. So we'll express this as the set of all x such that x is equal to our first positive solution, 1.5 radians, plus any angle coterminal with that one. So we attain those coterminal angles by adding one complete rotation, 2k pi, or 4.8 plus any angle coterminal with that. And once again, I'm going to specify that k must be an integer. Now note that you can certainly check this with your calculator. I'm going to go back to the original and I'm going to approximate cosine of 1.5. Now it's going to be approximate, but we can see it is about 0.1 when we round to the nearest tenth. In addition, we can see that cosine of 4.5 gives us approximately, that's supposed to be cosine of 4.8. That gives us approximately 0.1. So our first two solutions balance the equation, which means any angle coterminal with those solutions will also balance the equation. If you have been diligent to invest the time in learning the unit circle, here's where it's really going to pay off as we solve these trigonometric equations. For example 2, we're going to apply the same logic, but this time we're working with the sine function. And note that we're finding all solutions to the equation. So our first example is sine of x equals -1. We're going to isolate the argument by evaluating inverse sine of -1. This means that I'm finding all of the angles on the unit circle with a sine value of -1, and we know sine is associated with the y coordinate. Now there's only one location in one rotation around the unit circle where sine is equal to -1. The y coordinate is -1 at 3 pi over 2. And there's no other location on the unit circle that has a sine value of -1. So the solution to this equation, the first solution is 3 pi over 2. And I'm going to add a multiple of 2 pi to express all other angles coterminal with that one, and we will have then found all possible solutions to that equation. It is a conditional equation, yet it has an infinite number of solutions. Let's try example B. Sine of x is equal to 0. So x, the argument, is going to be obtained by evaluating inverse sine of 0. So we need all the locations on the unit circle where sine is equal to 0, or all the locations where the y-coordinate is equal to 0. We have a couple of candidates for solutions here. The y-coordinate at 0 radians, or 2 pi radians, is 0, and the y-coordinate at pi radians is also to 0. Now, we can be efficient with the way we express the solution on this one. Instead of expressing all angles coterminal with 0 and all angles coterminal with pi, we can observe that those angles are always pi rotations apart. For that reason, we can express the solution as the set of all x, such that x equals pi plus k pi. And you know, I think we can do it even simpler. Let's call it k times pi, where k is an element of the integers. So if k is 0, then x equals 0 is our first solution. As k is 1, x equals pi is our second solution. And then we would obtain 2 pi, 3 pi, 4 pi, and we're just rotating back and forth between these two terminal sides. So those are the solutions to that basic trig equation. Let's try example C. Sine of x equals square root of 2 over 2. So inverse sine of square root of 2 over 2 is how we'll obtain the solutions. So we are looking for an angle on the unit circle whose sine, or y-coordinate, is equal to square root of 2 over 2. Hopefully you're already thinking about the reference angle pi over 4. Because sine of pi over 4 is positive square root of 2 over 2 in quadrant 1, we have our first solution. But remember, sine is also positive in quadrant 2. Sine of 3 pi over 4 is also equal to square root of 2 over 2. So those will be the springboards for our solution. The solution then is the set of all x, such that x equals our first positive solution, pi over 4, plus any angle coterminal with pi over 4. In addition, 3 pi over 4 is a solution, plus any angle coterminal with 3 pi over 4. And as always, we'll be diligent to note that k is an element of the integers. So we have expressed an infinite number of solutions in a finite, efficient amount of space. Let's try sine of x equals negative 0.3. Once again, the argument that we're looking for, x, will be obtained by evaluating inverse sine of negative 0.3. Recall that we always look for the smallest positive solution on the unit circle first. I want to make a note here about the domain of inverse sine. Recall that the domain of inverse sine runs from negative pi over 2 to pi over 2, as we learned in the previous section. That will be important to keep in mind because we're going to approximate this solution with our calculator. When we evaluate inverse sine of negative 0.3, it's only going to yield a value in that interval. So let's go ahead and do that. We are in radian mode. We can evaluate inverse sine of negative 0.3. And our first solution, notice, is a negative number. Now I'm just going to round off to the nearest tenth here. So the calculator gives us negative 0.3 radians. But remember, in our algorithm, we always want to give our smallest positive angle first. So I'm going to need to convert this into a positive angle. We can do that simply by rotating from 2 pi back 0.3 radians. So this is also known as 2 pi minus 0.3 radians. I'm just going to approximate that with my calculator. Again, I'm just working to the nearest tenth here. So we can call that well, if we round to the nearest tenth, we'll have to call that 6.0 radians. So one solution is 6.0 radians. Now, let's seek out any other possible solution in one rotation of the unit circle. Notice the sine value here is negative, and we know that sine is also negative over here in quadrant 3. So I could figure out this one by taking pi radians plus a reference angle of 0.3. So pi radians plus 0.3 radians is going to give us approximately 3.4 radians. So we have two positive solutions in one rotation of the unit circle, and we use those as a springboard for all the solutions. So the set of all x such that x equals 3.4 plus any angle coterminal with 3.4, so we're going to add a multiple of 2 pi, or 6.0 plus any angle coterminal, and we will once again specify k must be an element of the integers for that to work. So those 8 examples that we just worked are basic trig equations. All of the other more complicated trigonometric equations will whittle down to something like those 8 examples. So let's try example 3, which requires a little bit more work up front. Notice the instructions here is to find all solutions, and guess what? We get to work in degrees. Yay, that's always good news. So the first thing we want to do is isolate our trigonometric function. So I'm going to begin by subtracting 1 from both sides. Then we can isolate cosine of alpha by dividing both sides by 2. And we're back down to a basic cosine equation. So to solve for alpha, we need to evaluate inverse cosine of negative 1/2. We are looking for an angle in degrees where cosine is equal to negative 1/2. Now recall, the range of inverse cosine is from 0 to pi. Just going to make a quick note of that. Range is 0 to pi. So inverse cosine is going to give us an angle either in quadrant 1 or quadrant 2. But we can sidestep the calculator here using our knowledge of the unit circle. We know that cosine is negative in quadrant 2, and we also know that at 120 degrees, the cosine value there is negative 1/2. So our first solution is 120 degrees. Now, if we are using our calculator to evaluate inverse cosine of negative 1/2, 120 degrees is the only answer that we're going to get. But we also know from our knowledge of the unit circle that cosine is negative also in quadrant 3. So at 240 degrees, the cosine value there is also negative 1/2. So we can now use those two angles as our springboard to express all the solutions to this equation. So the solution to this equation will be the set of all x such that x equals 120 degrees plus any angle coterminal with 120 degrees. I want to be careful here. I'm not going to use a multiple of 2 pi. I'm going to use a multiple of 360 since we're working in radians. So if I take 120 degrees and I add any multiple of 360, I will find another angle coterminal with 120. Let's do the same thing with 240. We'll start with 240. We'll add 360 times k to generate all of the angles coterminal with 240. So we have found every possible solution expressed in this finite way to that simple cosine equation. This one was simply different because we had a few more algebraic steps at the beginning, but then notice we whittled it down to a basic cosine equation. Let's try example B. Now on example B, we're going to need to isolate the sine function. So I'm going to subtract 3 sine of beta from both sides so that we can group all of our sine terms together. In addition, I'm going to move this constant negative 7 over to the other side. So we end up with negative 1 equals 2 sine of beta. Let's go ahead and divide by 2 in order to isolate our sine function. So negative 1/2 is equal to sine of beta. So we can now apply inverse sine to both sides. Inverse sine of negative 1/2 is going to give me a value of beta. Let's acknowledge the range of inverse sine in case you do decide to use your calculator. Negative pi over 2, whoops, let's work in degrees. Let's call that negative 90 degrees to 90 degrees. Probably should have done that over here too. Let's just make a note. When you're thinking in degrees, that's 0 to 180. Okay, we are looking for an angle on the unit circle, either in quadrant 4 or quadrant 1, that is from negative 90 to 90, whose sine value is negative 1/2. We know that sine is going to be negative in quadrant 4. Now, if you do inverse sine of negative 1/2 in degrees on your calculator, it's going to tell you negative 30 degrees, but we want a positive value. We also know that this is coterminal with 330 degrees, so we'll use 330 for our solution. So coming out of the range of inverse sine, we would obtain negative 30 degrees. I'm simply converting that into a coterminal positive angle because it's customary to use positive numbers in the solution set. Now don't forget, there is another location on the unit circle where sine is negative 1/2. Sine is also negative in quadrant 3. The angle here would be 210 degrees. I'm using a reference angle of 30 degrees. Okay, we've done the hard work. We're ready to assimilate our solution, the set of all x, such that x is equal to, I'm going to start with 210 degrees plus any angle coterminal with 210. We express that as adding a multiple of 360 degrees, or 330 degrees plus any multiple of 360 degrees. And as always, we'll specify that k is an integer. Whew, we did it. We got some basic sine and cosine equations solved. In the next video, we'll follow a similar process to solve basic tangent equations.